As you may remember from mechanics, the concept of potential energy proved to be very useful for understanding certain physical situations. In particular, potential energies were defined for a few specific forces, namely gravity and springs. These forces are called conservative forces because the work they do on an object as it moves between 2 points does not depend on the particular path between those 2 points, i.e., it only depends on the initial and final positions. Today, we will discover that the Coulomb force is another such conservative force. Let's begin by calculating the work done by the Coulomb force on a particle with positive charge Q2 when it is moved from a distance r sub a to a distance r sub b from a fixed particle with charge Q1 as shown. Since both particles have positive charge, the force on the moving particle is repulsive and points to the right. As we move this particle away from the stationary particle, the magnitude of the force decreases. Thus, to calculate the work done by the Coulomb force, we must perform an integral. In particular, the work done by the Coulomb force on the moving particle as it travels from A to B is just given by the integral from r sub a to r sub b of f sub e dot dr. Now, since the vectors f sub e and dr are always in the same direction, f sub e dot dr is just equal to f sub e times dr. We now use Coulomb's law to rewrite f sub e in terms of the charges of the particles and the distance between them. Integrating dr over r squared yields minus 1 over r, which evaluated between the limits gives us our final result. Namely, that the work done by the Coulomb force is proportional to the product of the charges and to the difference of the inverse distances. It's always a good idea to see if your answer makes sense before moving on. In this case, we know the work done must be positive since the force and the displacement are in the same direction. Both the force and the displacement point to the right. As we look at the expression for W sub a b, we see it indeed will always be positive since r sub a is always less than r sub b. In doing this calculation, we took the path to be along the line connecting the two particles. We now want to demonstrate that we would have gotten the same answer for W sub a b no matter what path we had taken to get from A to B.